Good afternoon.
Good afternoon, sir.
Shall I start?
Yes, sir.
Okay. How was the internals? How was the
Good,
internals?
sir.
Good? Okay. We're starting the third module, shear force and bending moments. This chapter is very easy if you understand. No formula, nothing. If you understand, this is the easiest chapter. You can get 20 out of 20 marks. If you don't understand, if you try to do merely just by substitution, you will end up wrongly. Then you will lose all the marks. Shear force and bending moments. We will discuss what is shear force and bending moment later. First, let us start. What is meant by a beam? Beam. We have looked into bars. That was first chapter. Now we will talk about beams. Beam is a structural member. Structural member which is subjected to transverse loading. For example, we consider this as the beam. Discuss different types of beam later. This is called a simply supported beam. Transfer direction since loading is in y direction or in z direction. There can be also special types like loading in x direction also, but we will not say that as beam. That becomes power. But when the loading is in y direction or z direction, when the beam is a structural member, when the loading is in transfer direction, we call it as a beam. Okay, call it as a beam. The other definition could be beam is a beam is a structural member meant to withstand bending loads. Beam has to withstand bending loads. There is a structural member. The axial member has to withstand axial deformation. Beam, for example, if I apply a load like this, beam will deform like this. It has to withstand bending load. That is, if I consider the axis like this, beam axis, then bending will be perpendicular to the longitudinal axis. The deformation will be perpendicular to this longitudinal axis. We call this as deflection. Why? This deformation will be perpendicular to this longitudinal axis. Always you should know. Okay. In case of beam, loading is in y direction, stresses induced in x direction, and deformation is in y direction. We'll discuss later when I come to the fourth model. Okay. So beam is a structure member which is meant to withstand bending loads. It should be rigid enough to withstand bending loads. Okay. And the different types of beams are, I'll call this types of beams. The types of beams can generally it is simply supported and based on the nature of support and loading we classify the beams. But he has given in some more elaborated way. We'll discuss this. Okay. First type. First type. Statically determinate beams. That is beams uh, for which the number of unknowns can be easily founded by using three equilibrium equations. Summation of force in x direction is equal to 0. Summation of force in y direction is equal to 0. Summation of moment is equal to 0. By using this three equilibrium equation, or generally force is equal to 0, moment is equal to 0. By using this equilibrium equation, if I can find the reaction forces, then these types of beams are called as statically determinate. For example, this is a simply supported beam. I have a reaction force RA at this end, RB at this end, RB, and if I have a point load here like this, I can find RA and RB by using two equilibrium equation. Summation of force in y direction is equal to 0. Summation of moment about point A is equal to 0. These beams are called as statically determinate beams. Okay. The next step would be statically or statically indeterminate, because it is statically this problem what you are dealing, all problems are static problems. It is not dynamic. The force is not varying with respect to time. These are called as static problems. Okay. Indeterminate problem, indeterminate beams. Indeterminate beams. If the number of unknowns, or if the reaction force cannot be finded by the by using the equilibrium equation, the number of the unknowns are more than the number of equilibrium equation. These types of beams are called as indeterminate beam. For example, in this case, there will be a reaction force RA, there will be an axial force RE, say RX, and there will be a moment like this MA. This is point A, this is point B. Assume this, there is a load like this, there is a moment like this MB, there is a reaction force RA, RB, and there can be axial load like this also, RB. So I have six unknowns which I cannot find by using my three equilibrium equation. These types of beams are called as indeterminate beams. Most of the beams what we come across are indeterminate beams. For simplicity, we will assume the beams are simply supported or cantilever like this. Okay. I'll explain this later. Different types of beam, simply supported cantilever. Time being, you understand the statically determinate and statically indeterminate beams. The next broad classification would be straight beams and vertical beams. Okay, that can be, this is very general. Uh, Next, the second classification would be simply supported beam. Simply supported beam, as the name indicates, the beam is just simply supported between two supports like this. Like this. It's just simply supported between two supports like this. This is simply supported beam. Okay, give me a moment. This is point A, point B, point C, point B. Generally, beams are represented just by straight line. It means to say that it is a beam. We are not taking the cross section. We are representing it just by a line. This is RA, RA, RB, RB, point T. Okay, this is simply supported. Generally, these simply supported beams are represented like this. It is represented by a pin support like this. This is the ideal representation by a pin support and a roller support at the other end. Okay, this is how this is the general ideal representation of a simply supported simply, even though this is one and the same as this, it will be represented by roller here. In case if there is a bridge and is simply supported, if there is some temperature delta T, it should be freely it should be free to expand in this direction. That's why the roller supports are provided. These supports are nothing but in this direction also it is fixed. When I talk about the support condition, it talks about whenever you constrain at any point, there will be the reaction force. Therefore, there is a reaction force Ry, Rx, and it is free to and to rotate in mz direction. Mx, My are constrained. Since it's 2D, I will leave it. It is free to rotate about z direction. Similarly, it is constrained about Ry. It is free to move in x direction. This simply support. Okay, simply supported beam examples can be uh, for example, let us say you are having two stones upon which uh, you have some slab like this. You have kept a slab like this. These are nothing of benches, what you see in parks or something like that. These are an example for simply supported beam. Okay. Now, second type, cantilever beam. If one end is fixed, the other end is subjected to load. Other end in the sense it can be anywhere along the length of the beam. If one end is fixed, generally we call it as if one end is fixed, other end is subjected to point load. We call it as cantilever beam. So what happens in cantilever beam? In case of simply supported beam, there are two polar reaction forces Ra and Rb. It is not subjected to moment. The two reaction forces Ra and Rb. Whereas in case of this cantilever beam, since it is fixed here, there will be a moment like this. Let me write moment ma, and there will be reaction force Ra, and there will be also a horizontal reaction force Rx like this. Okay, there are three unknowns or three reaction force coming into picture. Here two unknowns or two reaction forces. Example is a flight wing. Flight wing is an example for cantilever, and your hand is also an example for cantilever. Your hand, if you stretch your hand, it is like a cantilever. It is supported at your shoulder, and it is a cantilever. Okay. The next type of beam, what we can discuss, is overhanging beam. Overhanging beam. If this beam is supported like this, assume that is simply supported like this, and it extends beyond the support, and it extends beyond the support beyond the support, called as overhanging beam. Okay, and obviously this is a simply supported beam. Two unknowns or two reaction forces will be coming into picture. There can be loading like this P, and there can be loading like this P2 like this. The next type of beam is a continuous beam. Whatever the beam which you have discussed until now are with only two supports, if the beam is continuous with more than two support, we call it as continuous beam. This is called as continuous. Okay. Next type of beam are topped cantilever, cantilever beam. If one end of the, let me write it, topped cantilever beam. If one end of the beam is, this is a cantilever beam. This is a cantilever beam. At the free end, there will be a roller support like this, simply supported at the free end. This is called as proper cantilever beam. Okay. Next, we'll discuss the types of loads. Types of load coming are acting on the beam. The first simplest case would be a point load. We call it as a point load because when you compare to the area, surface area or whatever area of the beam, the load is acting on a small area. When you compare to the area of the beam, load is acting at a small point, very small region. When compared to this entire surface area, the load is acting at a small region like this. Hence the name, it is point load. Okay. This point load can be, for example, if in your hall, if you're standing on one of the tiles, okay, you are a point load for the entire in your entire your hall area, you are applying a point load on the ground. It is a point load. But when you keep for example, when you keep some slab on that, it is like a uniformly distributed, which we will discuss later. When you compare to the area, the load is acting in a smaller area. This is called as point load. For example, if you take the load from one more beam, if you take, for example, if the load is coming from some other column like this, there is one more column which is applying the load. For example, assume a multi-storied building or your college only. The load is coming from the other column on the beam. This is acting on a small area compared to the entire area of the beam, and it can be considered as your point load. Okay. Now the second type of load can be uniformly distributed load. Uniformly distributed load in the sense the load is uniformly distributed throughout the length. Load is uniformly distributed. For example, w kilonewton per meter or 5 kilonewton per meter. This is this much. For 10 meter, how much? That is 5 into 10, 50 kilonewton. So this is how you have to take w kilonewton. For example, if there is a pole like this, electric pole, and the wires will run like this. Due to wind load or wind gust, the entire length of the your electric pole is subjected to uniformly distributed load. Okay, and this is called as uniformly distributed load. Uniformly distributed load. Now, in case of uniformly distributed load, I will give an example. Let us consider simply supported beam. I will take the reaction as just taking an example, 10 and 15. Okay, and this is uniform. Okay, I will give without considering the values. I will take like that. Okay, it will be confusing for you. RA, RB, and this is also not required. A, C, D. Okay, 1 meter, 1 meter, 1 meter. Now assume that I am taking the moment at point D. I want the summation of moment about point D. How you would take, for example, say this is W kilonewton per meter. As I will assume my clockwise moment as positive, anti-clockwise moment as negative. So if I take the clockwise moment, RA, it is bending the beam like this. RA, this force is bending the beam like from this point. It is bending the beam like this. This is anti-clockwise moment. This is clockwise moment. RA into this distance is a clockwise moment. Okay, I can write RA, this distance RA into, this is a clockwise moment, RA into 2RA, and then this moment, when I'm talking about this, I am representing it here. See, always you should take the load is concentrated at the center of gravity. This is point C, this is point D. This entire load, the load is acting on, say, for example, let us take this as X only. This is a little confusing for you. X, let it be something X. So the load is, total load is the 5 kilonewton per meter into 5 meter. It is equal to 25 kilonewton is the load. Similarly, W kilonewton per meter on a length of X. This is Wx acting at the centroid of this, acting at the centroid between the location A and C. This is W into X. Okay, when taking the moments, moment about D is equal to 0. I will take RA into whatever X plus 1. Simply I am telling you, but you should understand. Simply in the sense I am taking, not taking exact value. Now this will cause an anti-clockwise moment. Anti-clockwise moment in the sense from this region. See this, if this is X, the centroid will be at X by 2 from either ends. So from this point also X by 2, this point also X by 2. So this is causing an anti-clockwise moment minus Wx, magnitude of the load, Moment is equal to magnitude of the load into perpendicular distance. Magnitude of the load into perpendicular distance minus W into X. Perpendicular distance to here is X by 2 plus 1. This is how you should take the moment. Okay, this will give the moment. For example, at point D, if you want, the Wx into X by 2 plus 1, 2 you should take. Okay, this is your uniformly distributed load. So you should always assume that when the problem is given with UDL, you should assume that the total effect of UDL is concentrated at a point called a centroid. When I have to take that centroid is at the center at that part, is centered at the center of that part, I have to take half of the distance from either end. So I'll be taking x by 2, x by 2. When I take the moment, load, magnitude of load or load into the distance. The distance is x by 2 plus 1, where I'm taking the moment this region, this entire distance I want. Okay, this is about your uniformly distributed load. Uh, the next type of load you might have been read in the engineering mechanics, uniformly varying load. Uniformly varying load. For example, let us assume a cantilever like this, subjected to a uniformly varying load like this. This is A, B, C, D. See, uniformly varying load, for example, let us assume uh, mm, so some snow is falling in certain region. And there is the tiles are mounted in a fashion like this. Due to accumulation of snow, the load is uniformly distributed. Sorry, uniformly varying. This is varying linearly. This is uniformly varying. This is just general example. There can be situation like your suspension bridge flyover, and the where load is uniform like this. This is the suspension bridge. Load is uniformly varying like this, uniformly varying load like this. Okay, the spring is here are subjected to that. This is a rope, and you can take an example for uniformly varying load. So how do you idealize this type of beam is, if you consider this beam, same previous concept for a uniform distributed load holds good. Uniform distributed load in the sense the magnitude of the load is uniformly distributed, is constant towards that length. Okay, uniformly varying load in the sense, for example, this is W kilonewton per meter. So the magnitude of this load, that is force in the for the uniformly distributed load, is half into is given by area of the triangle, half into B into H, half into, if I assume this as H, for example, this as X and this as Y, this is half into X into Y. Okay, and always you should note that in uniform distributed load also the load is concentrated at H. If you take this region, centroid is at a distance of H by 3 from this region, H by 3, and from this end, it is a longer end, it is at a distance of 2H by 3. 2H by 3. So I will take this point. So this region, this is B, this is C. From this region, H by 3 distance, a load of half into X by V is concentrated. If I want a moment about point D, summation of moment about point D, say RA, and this is, say some, I've taken as X, say some 1, then you can take RA, this is 1, RA into 2 plus X, this is clockwise moment, minus half into magnitude of load into perpendicular distance. Perpendicular, this is H by 3, this is point B, this is H by 3, and the remaining distance is 2h by 3. 2h by 3 in the sense, h by 3 in the sense, h by 3 in the sense, which is equal to x by 3. That is height 2h by 3 in the sense 2 times x by 3. Okay, this region is x, right? 2h by 3 is nothing but h by 3 is x by 3. 2h by 3 is 2x by 3 height. Okay, this, if you consider triangle like this is the height of the triangle. Hence, this is not, in our case this is x. Okay, half into x into y into 2h by 3, 2h by 3. That's one. This is how we should take. This is the uh, moment would point. So this is the case of this. In case if it gives the triangle in the other way, this is uniformly varying road. Point B, point C, point D, distance X. We should always assume the load is concentrated at the center. I've written the same sketch. We should assume the load is concentrated at the center. It is nothing but at this center. Wherever there is more load, centered will be at this point. So this is at this region. This is C. This is B. So this region from year to year will be 2h by 3. We can refer to your mechanics book. And this is h by 3 and this is D. Okay. And this is your magnitude of load off into x into y. This we consider y off into x. This can be for example, this can be 50 kilonewton. Then off into x into 50 you can take, or off into 2 into, if it is 2, off into 2 into 50, something like that. Off into x into y. If I take the moment about point t, summation of moment about t point is equal to 0, which is equal to, I'll just write this thing, off into x into y minus this anti-clockwise moment into h by 3, h by 3 plus 1. This is how you have to take. Okay. And okay, coming to the actual concepts of this chapter, whatever discussed was related to engineering mechanics, shear force, and bending moment. I will explain this with an example. Okay. Before that, let me give the definition. Shear force. It is the algebraic sum of vertical forces acting along one side of the section one side of axis of the beam, one side of the section. Okay, it is algebraic sum of vertical forces acting along, he has written like this, acting, okay, acting on one side, acting along in the, better than this, acting on one side of the section. I will explain this. Bending moment, it is the algebraic sum of moments acting on one side of the reference section taken. Let me put this reference section. So we will not understand just a statement. Let us consider a cantilever beam like this. I will apply a load P like this. In 10 minutes running, I will apply a load like this. Forget about the reaction RA and moment MA and the horizontal reaction RA, whatever. Okay. When I apply a reaction force, if I take a section at this region, if I analyze like this is P. For equilibrium, there should be one more vertical force like this. This vertical force, which is acting perpendicular to the suction, is called as shear force. This is called as shear force. Okay, now this force and this force is creating a clockwise couple. This force and this force is creating, this acting upwards, this acting downwards, it is creating a clockwise couple. In order for equilibrium, there should be an anti-clockwise couple like this anti-clockwise couple at the moment is called as bending moment. Anti-clockwise moment, a couple is called as, this is called as bending moment. Okay. Now, shear force in the sense, according to our definition, now it means to say that I am coming from, there is one, assume that there is one more force, P1, P2, there is a force here, P3. So I am coming from left to right, sorry, right to left. So algebraic sum of all these shear forces V, all these shear forces V from the left end is called as your shear force. For example, at this section, if I take CD, what is, if there is one more section? There is section X, X1, X2, X2 I have created here. What is algebraic sum of vertical forces at this region? This is the shear force at this shear force in this region. I will take the section here. Algebraic sum of shear forces in this region. That is P1, P2 plus P3. All this force if I take, this is the shear force at this region. So it's shear force in the sense I cannot. This is the internal vertical force. Shear force in the sense internal. This is the internal force. Internal force. Bending moment is also internal internal moment. Since it is difficult to find internal shear, internal force and internal moment, we take it with respect to the externally applied load. And always you should remember, we will not talk about this, but you should remember my shear force, whatever shear force diagram what we got, is there is opposite. Generally we will plot the shear force diagram with respect to load. So my shear force will be opposite to that. Similarly, bending moment will be opposite to that. Okay, so if I take this section throughout, if I add all these vertical forces, since it is difficult for me to take the internal forces, I will add these vertical forces at each and every section. This internal forces at internal vertical forces at each and every section gives the shear force. Similarly, bending moment, if there is a moment like this P2 into this, for example, if I want a moment at this point C, P2 into X, P2 into X, actually P4 into some, P4 is 0. Similarly, if I want a moment here, P2 into X plus Y, P4 into X, Y. So this gives the bending moment. So algebraic sum of moment I am taking from one side of the section, that is from right to left, is called as your shear force and bending moment. Generally, I will take from left to right. It is one and the same. Okay. Have you understood this? Have you understood this? Enough to tell me, have you understood this? Hello? Mikala, have you
Yes,
understood?
sir.
Right? Okay. Now, it is the
Yes, sir.
okay. It is the algebraic sum of vertical forces, because vertical forces there is external forces, internal forces difficult to find out. Algebraic sum of vertical forces acting on one side, that is the left hand side or right hand side. Bending moment is the algebraic sum of moments acting on one side, that is left hand side or right hand side, with that is bending moment. Okay, and give the same convention for shear force and bending moment. This is very important. You should understand this. 6 minutes, 5 minutes remaining. If this is my, this is my section XX, but you understand like this is my section. I am coming from left hand side towards right hand side. This is the section where I've taken, this is the beam like this, from left hand to right hand I'm coming. This is where I've taken the section. There is a force acting like this. If the force is acting with reference to my section is here, that is the right hand side, this is the right hand side, this is the right hand side, force is at the left hand side. If the force at the left hand side is acting upwards with reference to right hand section, this is called as pause, and then obviously this is left hand. If there is if you're coming from left hand side, then this force would be like this. This is called as positive shear stress. This is positive shear stress. We will understand when you solve the problem. So when I'm coming from right hand side towards right hand towards left hand side, if my force is acting, for example, if there is a force acting upwards like this, upwards like this, with reference to suction, which is at the right hand side, this is at the right hand side, force is at the right hand side, then this force is positive. This force with reference to right hand side suction, which is acting downwards, is negative. This force is negative. This is for the second case. This is for when you come from the left hand side. When you come from the left hand side, this force is to downwards and your suction is towards the left hand side, then this force is also positive. Okay, this force is positive. It will come from one side, any one side. Okay, now negative shear force. This is the, if I apply a load like this will go like this will come like this. Okay, negative shear force. This is opposite to that. This is my suction. In this case, this is the negative. My suction is towards the right hand side. Load is acting downwards when I come from left to right, and from if I come from right to left, the load is acting. If the load is acting upwards, and the suction is towards left hand side, this is your negative shear force. Or in other words, if it moves the suction like this is the suction like this. If it moves your beam like this is called as positive and negative shear force. Negative shear force. Bending moment. Bending moment. It is similar to that. Bending moment. Let us consider the beam like this. Okay, and this is the suction. Okay, XX. If it if the beam if the beam bends in this fashion, if the beam bends in this fashion, how it is possible? If there is a moment acting like this from the right section which is at the right hand side, if the moment is clockwise, and section which is at the left hand side, if the moment is anti-clockwise, this is called as positive bending moment. Always you should remember like this. Smiley face is positive bending moment. Okay, next, if I consider suction, this suction at some point, if my uh, beam is subjected to moments like this is clockwise, this is counterclockwise, and the beam will bend like this, like this, called as your negative bending moment, or your sad face is called as negative bending moment. This is negative bending moment. I am stopping at this point. Time is getting over. This is called as negative bending moment. From left from the suction, if there is a clockwise moment, it is positive shear force bending moment. From the suction, from the right hand side, if the suction is at the right hand side and the moment is acting in the counterclockwise direction, this is negative bending moment. If the suction is at the right hand suction and the